Hi everyone, welcome back. So in this video here, we're going to discuss another reaction of alkenes, and then later in subsequent video we'll see how this reaction applies to alkynes. Okay, so this reaction that we're covering is catalytic hydrogenation. And this is from section 8.8 in the textbook. So this is section 8.8 in the textbook. What this reaction does is it would convert an alkene into an alkane. Okay, so it would remove that double bond, carbon-carbon double bond. So it would convert an alkene into an alkane. And the alkene is formed with or this hydrogenation, it is a syn addition. Okay, the product has both hydrogens on the same face. Okay, so both hydrogens are added from the same face of the alkene. So again, realize that because the carbons in an alkene are sp2 hybridized, okay, wherever the double bond is, those carbons are sp2 hybridized. So it's a trigonal planar system over there. So it is flat. So that means anything that's adding, as in previous examples, anything that's adding to a double bond, so if these are two carbons that are double bonded, they can add from the top face or from the bottom face. Okay, or if the alkene is like this, if this is how the two carbons are and they're trigonal planar, then they can add from the front face or from the back face. Okay, so there are two modes of addition in every case. So we'll discuss this reaction. As an example again, I'm going to show two examples, one where we cannot really show this syn addition, and then another one where we can actually show this syn addition. Okay, so if we have an alkene and this reaction is done using hydrogen gas, so it's a hydrogenation, so that's addition of hydrogen. So basically H2, the two hydrogens, they're added to the alkene. And for doing this reaction, we need a catalyst. Okay, so the catalyst that's used here is a metal, usually a transition metal like platinum, PT, platinum, or palladium. You can use rhodium as well. So those are some of the metals that are used. Now, mostly people use platinum and palladium. Those are the most common metals that are used for doing these reactions. And there are other metals. Okay, this is just a limited scope that I'm giving here. So it uses one of these metals, and then we have the hydrogen gas. And so essentially, once we do this reaction, we get the alkane product. So we start with an alkene, and we get an alkane as our product. Okay. Now, obviously, in this particular case, we cannot really talk about the syn stereochemistry or the syn addition that we're talking about. So let's look at another example. So let's say if we have a cyclic system where we can actually see this syn addition, I think best, that's where we can see this. So cyclic system, let's say we have an alkene. And I think I want to take a few minutes here and talk about this alkene and how I would draw these groups, because that's something that I saw on quiz 7. That's something important that I want to point out. So these two carbons here, they are sp2 hybridized. That means and the way I've drawn this molecule, the ring itself, I've drawn it in 2 dimensions, okay, and I'm drawing the ring in the plane of the whiteboard, because all of these bonds are basically straight line bonds. Okay, so that means the ring here is in the plane of the whiteboard, and since these two carbons are sp2 hybridized, the geometry around them should be trigonal planar. And what that means is these two methyl groups here, they should also be basically in the plane. They should be straight line bonds, okay? I saw several examples while I was grading quiz 6 where these methyl groups on a molecule that we had, they were drawn using a wedge and then a dash like that. Now this really doesn't make sense, because when I look at this molecule as organic chemists, when we're trying to read this molecule, what we're seeing is a ring that's in the plane of the whiteboard. That's what these straight line bonds are supposed to mean, okay? And we have carbons that are sp2 hybridized, so they're, the geometry around them should be trigonal planar. And then what we see is that there's a methyl group that's pointing behind the plane of the board, and there's a methyl group that's pointing above the plane of the board, or if they're both wedges or both dashes, okay? That really doesn't fit the geometry requirement of the hybridized carbons here, okay? Because those carbons are sp2 hybridized. We want to draw everything in a straight line, okay? So this is incorrect, okay? This is incorrect if that's how we draw the molecule. Now, we could show wedges and dashes, okay, on a double bond. So for this particular molecule, although it's a little difficult, I'm going to show you another way of drawing this molecule where the wedges and dashes would make sense. I'm going to draw this alkene such that the methyl groups are both on wedges, okay, and then I guess this is too much of an extreme, but what I'm trying to show here is that my ring is on a dash. Okay, so I have the double bonded carbons here. The two methyl groups, they're pointing straight out. Okay, so they're pointing out of the plane of the board, okay, in front of the plane of the board, that's where they are. And the ring itself is behind the plane of the board. So now I'm looking at this ring from a very different orientation. Over here, we're looking at the ring like, okay, so that the methyl groups are over there and the ring is on this side. Everything is planar. In this particular orientation, we're looking at that ring like this, so that the methyl groups are now pointing towards us or towards you guys, and the ring itself is pointing behind the plane of the board, okay? So in that orientation, the wedges and the dash would make sense, but not in this orientation. So please keep that in mind, okay? So going forward, whenever you're drawing molecules, pay attention to the hybridization and think about what should be the geometry around that carbon. Very important to keep in mind, okay? Okay, so in this particular case, and you will see that here, as I work on this, I'm going to change the methyl groups. I'm going to change the sort of bonds, the kind of bonds they would be on, okay? So right now, they are straight lines, basically bonds, because everything is planar here, okay? At least around these carbon atoms, which are sp2 hybridized, every group that's connected to those carbon atoms should be planar. They should be in a trigonal plane, okay? So we start with this molecule, and let's say we do a hydrogenation. So I use H2, and let's just use one of these metals, okay? Let's say it's platinum. And again, always, as you practice, try to memorize one of these combinations, but you should be able to identify every combination, okay? Key here is look for the hydrogen. So when you see an alkene and then the hydrogen and there's some metal there, let's say, it could be platinum, palladium, rhodium, nickel, any of those things. When you see a metal, think about hydrogenation, okay? So we're doing this hydrogenation, and now, as we said, this is a syn addition, okay? So both hydrogens add from the same face, and so if both hydrogens add from the front face on this alkene, then my product, if both hydrogens added from the front face here, okay, both hydrogens come and add from the front face of this alkene, then the product that I get, or that we are going to get, is going to be this molecule. So notice how I've now changed the methyls from straight lines to dashes. That's because the hydrogens themselves added from the front face. And those are not shown in the bond line structure, but on these carbon atoms. These are now sp3 hybridized, okay? And so the hydrogens are on wedges on both carbon atoms. So that's one option. And plus, the hydrogens could add from the back face, okay? They could add from behind. And if that's the case, then both of these methyl groups would now be on wedges. So this is the syn addition that we're talking about. Okay, so this is a syn addition. That means both hydrogens add from the same face. So this is a hydrogen. This here is a hydrogen. This is a hydrogen. This here is a hydrogen. And you don't have to show the hydrogens, because as long as you show appropriate stereochemistry for the other groups, the hydrogens are implied in the bond line structure, okay? So that is the product that we're going to get. Okay, so now what we'll do is let's just quickly look at a mechanism for this reaction. Okay, so this reaction here, okay, something that I want to point out is, because we're going to look at another variation of this reaction, is that this particular way of doing reaction, or these catalysts here, these are called heterogeneous catalysts. Heterogeneous catalysts, okay? And what that means is that the catalyst here, again, when you picture this, when we do this in the lab, you know, you must have a round bottom or some sort of a flask where you have your alkene. There's probably a solvent, okay, and then you have hydrogen, which is a gas. So you're basically bubbling in hydrogen gas, pressurizing the whole system with hydrogen gas. So these reactions are usually done in pressure reactors, systems that can hold high pressures, okay, pressure reactors. And then you have your catalyst. So the catalyst here does not dissolve in your solution or in your system, the solvent, okay? So the catalyst actually stays outside. So that's why this is called a heterogeneous system. Now we're going to see a homogeneous system later, okay? So these are heterogeneous catalysts, and this is heterogeneous catalytic hydrogenation. Okay, and so because these are heterogeneous, the mechanism that we're going to see here is going to be unlike other mechanisms that we've seen so far, okay? So one way to just picturize this is to, let's say that, okay, this is our catalyst, okay? So this is catalyst. This is the catalyst. So when hydrogen comes in, the hydrogen gas interacts with the catalyst. And when it does that, this hydrogen atom breaks up, and hydrogen atoms they get adsorbed, okay? So they get adsorbed on the surface. So this is not absorption, okay? So it's unlike absorption, because absorption, like a sponge, when it absorbs water, it is like a bulk phenomenon. And what that means is the water gets inside the sponge. It's like everywhere in that sponge, or anything when you soak something, it's like everywhere. Adsorption is more like a surface phenomenon. When something is adsorbed onto a surface, it's not getting into the bulk of that material. It's not inside, but it's only on the surface. So it's a surface phenomenon. So adsorption, a surface phenomenon, that's what's happening here. So the hydrogen atoms, as they interact with the catalyst, they break up and they get adsorbed on the surface, okay? And from here, you can imagine that the alkene comes in, okay? And as the alkene comes in, it interacts with the hydrogen atoms. So one of the hydrogen atoms is going to get added to the alkene. So we'll get to a situation where we have a hydrogen, and again, the addition would happen at the less substituted site here, okay? So we will get a situation like this, where one of the hydrogens has added to the less substituted carbon, the alkene is basically attached, and then the other hydrogen, okay? So one adds first, and then the other one adds. Okay, now, and once you get this, then we get the catalyst back, the catalyst is regenerated, and then the alkene, and we get the alkane. Okay, and so we get the catalyst plus the alkane. So very crude way of representing this, I would say. Okay, it's very crude, but because the alkene comes and interacts with this catalyst where the hydrogens are adsorbed onto this catalyst surface, both hydrogens add from the same face of the alkene. Okay, so if this is an alkene, as it comes and interacts, they both add from the same face. So that's the thing here. That's the mechanism basically here. Okay, so this is heterogeneous catalytic hydrogenation. Now, like I said, you can also do this homogeneously. That also gives you syn addition. So homogeneously we use other catalysts. Again, one example that we're going to see here is so homogeneous catalyst. Okay, so look at one example of a homogeneous catalyst, like the most common one, the most popular one. So this catalyst is based on a rhodium metal. So again, we need hydrogen because that's what's getting added. And the catalyst here is this complex. This is called Wilkinson's catalyst, okay? And it's based on rhodium. That's the metal here. And this again would give us syn addition, but the alkene becomes an alkane. So if we used that cyclohexene based molecule, then the alkene would become an alkane. So do some examples, practice a little bit, but again, it is one of the simplest reactions. All you have to remember is alkene becomes alkane. Important thing is whenever stereochemistry is important, the hydrogen adds from the same face. Okay, that's what you have to remember. Actually, by the way, I forgot to point it out. In the cyclohexane example that we did earlier, the two compounds that we made, they were both identical because they were meso compounds. Okay, those products were both meso, so that means they were the same compound. Okay, I wanted to point it out at that point, but I left it out. Okay, because those compounds have a plane of symmetry. Okay, so that's catalytic hydrogenation. Okay, bye.